I'm Ofer Dahan. I'm from the Ben Gurion University of the Negev in Israel. I am the CTO of Sensoil, which this is the technology I'm going to talk about. And I'm going to talk about the application of Vadose Zone Monitoring Systems as a key to groundwater protection and optimization of remediation strategy. But before I plunge into the technical and scientific stuff, let me say how lovely it is to wake up in the morning in a cool place, green grass and gray sky. Because where I live, usually the landscape is brown, the sky is blue, and the air is super dry. So it's a different atmosphere, but anyhow, we are here. So allow me to start with something which is redundant to all of you. You all know it, I know, and I'm going to waste 2 minutes of your time on things which you all know. Groundwater, located under the unsaturated zone, is the most important source of water. Yeah, we know it. And in recent years, more and more we talk about water scarcity. But as we talk about water scarcity, we forget that on a global scale, 80% or even more of groundwater pollution creates the main reason for freshwater scarcity. Okay? More than anything that we know about climate changes. We know climate changes may do things, but on a daily basis we lose more and more water due to groundwater pollution. But when we talk about groundwater pollution, let's see first the process. And this is also something which is very known. So we know that contaminated originate on land surface, whether it's from the agricultural sectors, pesticide, herbicide, whatever, industry, infiltrates through the unsaturated zone and penetrate all the way down to the groundwater until it accumulates in groundwater. Only that when it accumulates in the groundwater, it's already there. So whenever we try to understand what were the processes that carried the pollutant from land surface to the water table, usually we will bring a drilling rig, as we all know it is. We will collect the samples. These samples will help us to create profiles of whatever we measure in these soil extract. And out of these soil extract, we try to understand what's happening down there. But these are nothing but snapshot in times. We know what is the situation there now. We don't know how we got there. And we don't know what the next rain of tomorrow will do to this profile. So all that is nothing, no dynamics. The other common method is using boreholes, as we all do, borehole observation wells. And these boreholes allows us to collect water samples. And we measure and monitor and monitor and monitor. There's tons of stuff out there to measure parameters in the groundwater. But unfortunately, until we find something in the groundwater, it crossed the entire unsaturated zone, accumulated in the groundwater to some kind of a plume, and this monitoring will bring no hope for this aquifer since it's too late for this particular aquifer. So monitoring in the aquifer in order to prevent groundwater contamination will give us nothing than a post-mortem for this aquifer. And the problem, since current remediation technology today are incapable of fully remediate groundwater to drinking water standards, it means that only if we monitor the unsaturated zone, the zone through which water moves to the groundwater, can bring some hope to the groundwater and protect it from pollution. So how is it done? The technology we have developed, Sensoil, is based on a monitoring sleeve that goes in slanted holes distributed through the entire cross-section from land surface to the water table. It contains monitoring units that gives us continuous information about the quality of the water as it's moving down, and also a hydraulic parameter that tells us something about how fast the water is moving down. The monitoring units include special water content sensors, which is practically the driving force for water to move in the unsaturated zone, but also gives us special sampling pods that allow us to collect liquid sample from unsaturated sediment from the entire domain. All this data, including the water samples, go from down to a dedicated control panel. In this dedicated control panel, we collect all the important data, but also water sample that can be analyzed for whatever chemical you're interested in, isotopic composition or whatever you want to do. And most of this data goes directly to the cloud, can be reached anywhere. From my computer, I can see data now from Israel, from Australia, from Belgium. We stopped, the link is stopped, but from other sites. And we can know what the rain of yesterday did to the unsaturated zone today. So practically by the end, if we have a net of units distributed in the desired zone, we can tell something about the quality and the quantity of the water as it's moving from surface down below with a system that I won't talk much about the nuts and bolts, but if someone is interested, I'll be happy to explain what it is later in the book. It is installed worldwide. We have those installed from China and Australia to the US. This continent is still on the way, on the go, in a variety of projects. Infiltration from steam channels and reservoirs, land use impact on groundwater quality, different type of agriculture, different type of industry. I'll give you samples, data samples from that later on. Landfills, we are talking about landfills, how leachate generate and propagate from the top of the heap, the waste heap, all the way down into the groundwater below. What is the chemical transformation of the leachate as they move down. In this conference, we talk a lot about pollution, and we love to blame the industry for groundwater pollution, but in fact, 85% of groundwater pollution or well shutdowns all over the world is just because of nitrate comes from the agriculture and not from the industry. So when we took groundwater pollution, not always the green part is the good part. In the landscape. Similar project in Switzerland, in the US, water balance in forested area, 1 day of installation, the next day the control panel is set and the data is already in the air and water samples already collected. So with this in mind, I would like to show you, or before that, today we have a large project, the current project we have now, we are going to put a monitoring net over the island of Malta. It's a small island with small natural water resources because of the size. And it's very critical for them to know what the agriculture is doing to the groundwater before. So we are going to use a net of monitoring system all over the island that will give direct information and real-time information about the quality or the link between the agriculture, different type of agriculture, to the groundwater below, long before it accumulates in the groundwater and makes it impossible actually to fix it. Now I'd like to give you a few examples from real data from different projects. And these projects will be, the first of them will be in-situ remediation of a contaminated site. So we know how industrial site looks like. I mean, this is a typical one, but from the figure you know what it is more or less. So in order to do bioremediation of the unsaturated zone, we need in the soil moisture. The bacteria wouldn't do anything without moisture. So we must know what is the moisture status in the subsurface or the profile. We need to make sure we have enough nutrients in the soil or in the deep unsaturated zone. We must know that the redox conditions are appropriate to degrade the exact type of contaminant we got from this kind of industry. We must also know that we have enough degrading bacteria there, otherwise nothing will happen. And we must give some food to the bacteria. These are the electron donor or electroreceptor that will do the work for us. So we must make sure that all these conditions exist down below this site if we want to go for in-situ remediation. So the common method is, how to say, poke holes and hope for good. We do it a lot. Making holes, collect samples, and do what we can do with the normal. But we came up with a different approach, which we are using now more often. And the approach is so. If we have a site that is contaminated, and we need to do in-situ remediation, usually we'll need to inject water into the soil. Water, amended water, and this amended water, while moving down, will change the chemical composition of the unsaturated zone. Now this can be few meters, or if you're in the Netherlands, you have less than few centimeters sometimes. But on the way, we need to encourage the bacteria to do what they need to do. But we know what's supposed to be there, we don't know it's happening there. So we propose putting a monitoring system that will give us real-time information about the quality of the water, or whether whatever we applied on surface reached the depth of interest. Have we really changed the chemical composition of the water down below here to make the bacteria work? And with this in mind, we could change continuously the characteristics of the surface to enhance it down below. So how is it working? For example, in this site, we have a site that is heavily polluted with perchlorate. It's in Israel somewhere. The site is covered with plastic sheets and soil to make sure that the area will get a reducing condition, because we must have reducing condition in order to degrade the perchlorate. We have a subsurface irrigation system in order to inject into the soil amended water. We have the monitoring system in order to see if what we actually planned happened. And now this is how data looks like. This is typical data. What we see is changes in water content in different depth over time. Without going into detail, I can say that every wave or a bump that we see here means that the water that we injected on surface reached to certain depth. So we can know by the changes of the water content how fast the water is moving. This is part of it. We know the moisture. Now we would like to see if we really degraded the contaminants. So here is a typical kind of results. What we see here is profiles. The data is now, we can present it in different forms, but here it is as profiles. This is depth in meters, and these are the concentration of perchlorate in logarithmic scale. And the first one before we started is the blue one. So you see concentration from hundreds to thousands of milligrams per liter. In some places it's very, very, very toxic, okay? But then immediately as we start with the infiltration of the amended water, we see concentrations start to drop down to practically zero. So if you're a consulting company or the remediator, this is the payday. Because you can prove that by that time, you clean the unsaturated zone without the need to bring it to another drilling rig, excavator to see what's going on. You see this in real time and online. But this is if you are the remediator. But if you are from the Environmental Protection Agency and you have such a system located under, I'll show you the data from on. The data that we show here is only the upper 12 meters, okay? What we can see, the deep below, concentration only been rising up, even in the groundwater below. Okay? So instead of remediating or biodegrading, what we did is just push down. This allowed us immediately to stop the operation and tweak the parameters on the surface in order to change the conditions here to get the exact condition that we are expecting below. I won't go into detail, but we have changed the way of method. We've changed the electron donor, the way it is implemented, and other parameters until we tweak the condition to make sure we get exactly what we care for in this part. So this is a way to optimize remediation condition of contaminated sites. It's been used in a variety of other locations. The other one was perchlorate, but we did it in remediation of the unsaturated zone under a gas station. There are also publications on these different kind of gas station, different type of fuels. And we also are now in a project of remediating an area which is contaminated with crude oil under a desert environment. Wherever there is an oil pipe, from time to time there are spills. Some tractor made some whatever it did and created these spills. So this is another type of project we are running for remediation by using the Vadose Zone Monitoring System to enhance the remediation. I'd like to show you now another type of typical project. And this is related to the greatest polluter on Earth. We need the food, so we need them. But we also need the groundwater below here because this is the main water source. But there is a link between them. And how is it going? So we had few projects, and this is the typical site, or actually it was supposed to be the clean site. I'm showing it because probably it's not the cleanest site. We installed a system. This is 18 meters deep down. 18 meters, it's like a 6 stories building all the way down. And I'd like to show you the kind of data. Let's start with the first sensor in 1 meter. And this is data showing the blue bars are the daily rain over a few years, from 2009 to 2014, but it goes on. And in the red spots, what we get is the concentration of nitrite over time. So you see that at the beginning it starts to rise up, and then it starts to go down, but rising up is to extreme concentration of 3,000 milligram per liter. As you know, the limit for drinking water is about 50 milligram per liter, depend on the country, depend where, but this is huge concentrations. So if you are the farmer or wherever you are, you say, okay, it was going up, probably there was plant uptake, and now we see the reduction in concentration. This is fine. But if you will look down, this is the data I just showed in 1 meter. Let's now go to the one below at 2.7. What we see that once concentration is drawing down here, down below, it's rising up. So something has pushed it down, and we can go further to depth of 4 meters and 6 meters and 9 meters. Year by year, it keeps on going down, and even at 18 meters, just 1 meter above the ground level, where concentration was 0, start to rise up. So I'm telling you all this story just to demonstrate how we can track contaminant migration from land surface to the groundwater. And long before groundwater is already contaminated, we can give indication to whoever needs the data, listen, there is something going up in there before it's too late. Another example, okay, this is the process I just explained. Another example, which is a picanteria, how we call it, is the impact of intensive organic agriculture on groundwater. In Europe and also in Israel, we love to buy organic food. We think it's good for Mother Earth. We think it's good for our tummy or whatever. And we pay a lot of money for organic farming. So we went to compare different type of organic farming. And this is the kind of result we got. This is concentration. I mean, we had two type of farms: conventional, which use drip irrigation and commercial fertilizer, and organic, which use manure or compost as the main fertilizer. What we see here in the conventional, that concentration of nitrate is very high, close to the surface, where we need it there. This is the fertilizer. It's supposed to be in the root, and down below, very low concentration. You can see we can take sample every how often we want. Every how much money we have to do analysis, because analysis costs money, but every 3 to 4 weeks I send a student to take a sample. So this is the healthy situation: high concentration in the soil, low concentration in the unsaturated zone below. If we go further to the organic farming, now you can see it is a catastrophe. High concentration reaching more than 600-700 milligram per liter of nitrate. Actually, this peak, this was in 2012. This peak is already here. Actually, touch the ground. We have a flat line going from the surface with 600 milligram per liter down here. So this is organic. This is conventional. And there are reasons for that, and we won't go into it. If someone is interested, I'd be happy to explain. There's several publications of that. But the reason is that on the conventional farming, no farmer will waste fertilizer to a plant which got no roots to either uptake the nutrient or the water. While in the organic, they have to implement everything in the soil before we plant. Then you have to put a lot of water to make sure that the nutrient will be available. Then it's exactly what happened when you put water to the pot at home. You just go down to a place where the plant cannot take it anymore, and you have extreme contamination of groundwater by pollution. So next time you buy organic tomato, think of it again, please. Another type of application, we are going back to industry. By the way, agriculture is an industry, but we're going back to the industry. This is another typical application we've been using a couple times to measure what's happening under sedimentation pond. This is in potash mining. In the production zone. The production zone needs the surface area to sediment the gypsum. And we installed such monitoring systems under the pond, either to make sure there's no leaks, or if there are no leaks, to measure the extent of it. So this is how it looks like. Data on how fast the water is moving down, and what is the chemical composition, as we just said a couple of times already, is diverted to a control panel located outside. This is how the installation looks like: a drilling rig, drilling diagonal holes, big mess around outside. At the end, what's left is a control panel located away from the system, and giving us all the data, liquid samples from, this is a desert area, collected here, and some of the data go directly to the outside. And this is the kind of information we get. The manager of the site can know in real time what happened to the water, in what depth they reach some critical values. These data actually go directly to the Ministry of Environment Protection in Israel, so they can. They are the big guy over this site manager. So there is a dialogue between the manager of the site to those responsible for the groundwater quality below. And I could go on with many more examples, as we have more than 100 systems like that installed over the world. And I would like to end up with a take-home message which will summarize what I just described.
Water is the source of life. Groundwater is the world's most important source of water. It is vital to ensure that groundwater is clean and uncontaminated by pollutants. Groundwater is usually polluted by contaminants originating on the land's surface, transported by water percolating through the unsaturated zone to the water table. Early detection of pollutants in the unsaturated zone is critical to save groundwater and other water resources. Existing monitoring programs based on groundwater sampling methods are ineffective, since pollution is only detected once it reaches the aquifer. Therefore, monitoring of the unsaturated zone is critical for protection of water resource quality. Sensoil presents the first ever real-time Vadose Zone Monitoring System, VMS. The VMS is composed of flexible sleeves hosting monitoring units, implemented in uncased, slanted boreholes. These enable continuous measurements of variations in the hydraulic and chemical properties of the unsaturated zone. The monitoring units include flexible water content sensors and Vadose Zone sampling ports. The system measures water flow and contaminant migration from land surface to the water table. Real-time hydraulic data and water samples for chemical analysis are continuously collected and registered by a dedicated control panel. Data from the unsaturated zone is directly accessible via cloud from anywhere. Once installed, Sensoil's monitoring system provides real-time information on pollution potential. This enables effective management and protection of water resources. Sensoil's typical water resource management applications include protection of groundwater from potential pollution, remediation of contaminated sites, water reservoirs, and enhanced safety of earthen dams. Let's protect groundwater, the global source of life.
That's about it. I could go on for hours to talk about it. Thank you.